Hey guys, this is Mrs. Harbin, and this is our final video on factoring for advanced math. We've talked about factoring when the leading coefficient is 1, factoring quadratics when the leading coefficient is not 1. We looked at some special factoring patterns, and today we're going to kind of combine all of that together and make sure that we have factored these expressions completely. For our lesson opener, let's go ahead and review what you've done so far by factoring each of these expressions. I do want you to pause the video and try these 5 on your own, then resume the video when you're ready to check your work. All right, in 6x plus 12, the greatest common factor there was 6. When we factor that out, we get 6 times x plus 2. In our second expression, x minus 5 was the common factor. When we factor that out, we get x minus 5 times x plus 7. In x squared minus x minus 12, we can use our little shortcut if we wanted to, or we could factor by grouping. Either way, we should end up with x minus 4 and x plus 3. We were looking of two factors of negative 12, that when multiplied equal negative 12, but when added equal negative 1, and that's how we got the negative 4 and positive 3. X squared minus 81 we should recognize as squares here, perfect squares, so this is a difference of squares, and that factors to the two conjugates, x minus 9 and x plus 9. And x squared plus 2x plus 1 is a perfect square trinomial, and that's going to factor to the square of the first, sine of the second, square root of the third. So we have x plus 1 in parentheses and squared. So that uses all of the different things that we've learned about factoring so far. When you are factoring expressions, you want to make sure that you factor completely. Some factoring involves numbers that are not integers, and we consider a polynomial completely factored when it cannot be factored further over the set of integers. So when there's nothing else that can be factored, we're going to consider that factored completely. In order for a polynomial to be factored completely, each polynomial factor, each factor that we create, must itself be completely factored. Let's take a look at what we mean by that. So let's start by factoring 5ax to the 5th minus 5axy to the 4th. The first thing that we're going to do is factor out the greatest common factor, which is 5ax. That leaves us with x to the 4th minus y to the 4th. Now we're not done yet because we can still factor x to the 4th, y to the 4th. That is a difference of squares. That's x squared squared minus y squared squared. So we can use our difference of square patterns here to get x squared plus y squared and x squared minus y squared. Remember, when we factor a difference of squares, we do create conjugates. Now you may think we're done, but we're not quite done yet. We have another difference of squares, x squared minus y squared. So we need to factor out that resulting difference of squares as well. And that again creates a set of conjugates, x plus y and x minus y. That's what this became when we factored it. The x squared plus y squared, a sum of squares, doesn't factor into real numbers, so we leave that alone, and we're left with 5ax times x squared plus y squared times x plus y times x minus y. At this point, we can consider this completely factored. We can always be sure to check our work by multiplying it back out. We can FOIL these, multiply those together, multiply that against that, and multiply that, then the result against 5ax or with 5ax, and it will get us back to our original expression. Let's factor x to the 4th minus 9x squared plus 8. We want to make sure that we factor it completely. Note that each binomial is going to start with x squared. So this is x squared squared. So there's our quadratic term. Here's 9x squared to the 1st, so there's our linear term, if you will. And then we have our constant term. So we can factor this just like we did before. We're going to split our first term into x squared and x squared. Then we're going to look for two factors of positive 8 that when added equal negative 9. And we get negative 8 and negative 1. Now we're not quite done just yet because, again, we have a difference of squares. This is x squared minus 1 squared. So we're going to factor that using our factoring pattern for a difference of squares, which creates conjugates. So we have x plus 1 and x minus 1. 8 is not a perfect square, so we don't have to worry about a difference of squares there. This is now considered completely factored. We can multiply it back out to check our work, and we would get x to the fourth minus 9x squared plus 8. Let's go ahead and try to factor 2xy minus 7x plus 10y minus 35. Now there's no common factor between all four terms, so we're going to go ahead and factor by grouping. We'll group the first two and the last two terms since there's no common monomial and there's no special pattern. So by grouping the first, we get 2xy minus 7x. You can see x is our common factor. And 10y minus 35, it looks like 5 is going to be our common factor here. So we'll factor a common monomial from each binomial, and we do get x times 2y minus 7. And when we factor out our 5, we get 2y minus 7. This should look familiar. Our factors in parentheses, 2y minus 7 become one of our binomials, and then what's outside the parentheses, x plus 5 becomes our other binomial. So we have x plus 5 times 2y minus 7. So there were no special patterns there, we just had to factor by grouping. If we FOIL that back out, multiply it back out, we will get back to our original expression. Okay, let's try to factor this completely. am minus an minus pm plus pn. There are no special patterns, so we are going to factor by grouping. We'll group the terms with a common factor. In this case, we can just split right here because they have a common factor of a and they have a common factor of p. So group the terms with a common factor and then factor out a monomial from each binomial, depending on what they have in common. Our first binomial has a in common, so we factor that out. And our second binomial has a p in common, a negative p, so we're going to factor that out. If we didn't factor out a negative p, our binomials in parentheses wouldn't match exactly. It would be the negative m plus n. But because we factored out a negative p, we've got a positive m and a negative n. So our parentheses here do match. That becomes one of our terms, one of our binomial factors. We have m minus n and then times a minus p. That becomes our other binomial factor. When we multiply that back out, we do get am minus an minus pm plus pn. So we did factor it correctly. Let's try another one. Factor 2y cubed plus 5y squared minus 8y minus 20. Again, we are going to factor by grouping because there are no common monomials and there are no special patterns. So we're going to group 2y cubed plus 5y squared plus a negative 8y minus 20. Go ahead and try to factor the rest of that one on your own. Pause this video to do that. Then resume the video when you're ready to check your work. Right, from our first term, we're going to factor out a y squared. And from our second grouping, we're going to factor out a 4. We then end up with y squared minus 4 times 2y plus 5. But is that the final answer? Hopefully you recognize y squared minus 4 as a difference of squares, so we do need to go ahead and factor the difference of squares, which is going to give us two conjugates. We get y minus 2 and y plus 2. A difference of squares factors as two conjugates. Square root of the first term becomes the first term in your two binomials, and the square root of your second term becomes the second term in the two binomials. So now we are completely finished factoring that. We can multiply that back out and make sure that it works, and it does. All right, guys, so that was just a quick look at putting all of these different factoring tips and tricks together, recognizing special patterns, factoring by grouping, using A times C to sum up to B. We put it all together in one quick review of factoring. If you have questions, write those down, go back and watch the video if you need to, and then bring any questions that you have to our next class.